In this video, I'll show you how to solve the ALEKS problem called Finding a Molecular Formula from Molar Mass and Elemental Analysis. There are actually quite a bit of steps involved in solving this problem, so you are going to want to work kind of carefully. This is definitely a problem that you want to make sure you get right on the first try. So the first thing that we're going to do is grab some atomic masses from the periodic table. We're going to want the atomic mass for all of the elements that have been given to us in the problem. So that's what I'm going to copy down right now. Carbon is 12.011. We also have hydrogen and we also have oxygen. Oxygen is 15.999 and hydrogen is 1.008. And that's all the information that we're going to need from the periodic table. Now, what we're going to do with this problem, we're going to start by determining the empirical formula of the problem. That's always going to be the first step here. Even though it's asking us for the molecular formula, we can't jump straight to the molecular formula. So the first thing that we're going to do is take these percents and we are going to think about them as grams instead of as percentages. Like that's going to be kind of a shortcut with our calculation. And we're going to convert each one of these masses, so the 62.58 grams of carbon, we're going to convert that into moles of carbon using the atomic mass of carbon from the periodic table, 12.011 grams of carbon per mole. And that is going to be 62.58 divided by 12.011. That is going to be 5.210 moles of carbon. We need to do this for every single one of the elements in this compound. So next up is going to be hydrogen, 9.63 grams of hydrogen, 1 mole of hydrogen. Atomic mass is 1.008 grams. And so that is going to be 9.63 divided by 1.008 is 9.554 moles of hydrogen. And then last we have our oxygen, 27.79 grams of oxygen. Use the atomic mass. 1 mole of oxygen is 15.999 grams of oxygen. And so that is 1.737 moles of oxygen. So this is going to be our mole to mole to mole ratio. Kind of as a reminder, as a visual, what we have figured out is that we have our empirical formula is C 5.210, H 9.554, O 1.737, and this doesn't work because these are not integers. We want our subscripts to be integers. So to turn these into integers, we're going to look at all three of our mole values. We're going to find the one of these three that is the smallest. The smallest is the 1.737 moles of oxygen. And we will divide every number by 1.737. So what we're doing is basically taking that smallest number and we're turning it into 1. We're dividing everything by that same number so that we don't disrupt the ratio of the carbon to the hydrogen to the oxygen. 5.2 divided by 1.737 is 2.999 moles of carbon, which is really close to 3. So we're just going to call that 3 moles of carbon. If it rounds to that integer, then we're just going to do that. 9.554 divided by 1.737 is 5.500 moles of hydrogen. We're not rounding that one. And then oxygen is going to be 1. Sometimes when you get done with this step, all three of these numbers are integers. In this case, they're not. So at this point, if one of your numbers is still not an integer, then the next thing you want to do is start multiplying. You're going to start multiplying all of the numbers by 2, and hopefully that's going to turn them all into integers. If it doesn't, you're going to undo that calculation, back up to these numbers, and try multiplying everything by 3 and see if that works. And if it doesn't, you'll back up and try 4. But you always want to start with 2. So we're going to try multiplying everything by 2. If we do this, we end up with, I'm going to switch colors, 6 moles of carbon. We end up with 11 moles of hydrogen, so that ends up being an integer, and 2 moles of oxygen. What we have figured out for this is the empirical formula, C6H11O2. Now that is not what the problem is asking for. It wants the molecular formula. The empirical formula is the smallest ratio of atoms. The molecular formula could be C6H11O2, or it could be twice that, C12H22O4, or maybe it's 3 times that, C18H33O6. And we can continue if we wanted. So the empirical formula is the smallest ratio, but the molecular formula could be anything, including the same as the empirical formula. The way that we're going to figure out what the actual molecular formula is by looking at the molar mass. We know the molar mass of our compound is 230.3, so let's just calculate the molar masses of these different options that we have until we come up with one that is 230.3. We'll start with C6H11O2. I'm going to leave myself some space here. The carbon atoms, 6 times 12.001. What am I doing here? I'm adding up the mass of all of these elements. The 6 carbon atoms, which are each 12. The 11 hydrogen atoms, which are each 1.008. And the 2 oxygen atoms, which are each 15.999. And we'll see what that gets me. 6 times 12.001 plus 11 times 1.008 plus 2 times 15.999 gets me 115.092. That does not match up with 230, so I know that this is not my molecular formula. Now, depending on how comfortable you are with math, you might be able to say, oh, that's 115, this is 230. This 230 is 2 times 115, so that means this must be it. This must be my empirical formula. But let's just say maybe you're not comfortable with that, and so we're going to try this guy right here. We're going to calculate the molar mass of C12H22O4. So instead of having 6 carbons, now we have 12. Instead of having 11 hydrogens, now we have 22. And instead of having 2 oxygens, now we have 4. Let's see what we get. 12 times 12.001 plus 22 times 1.008 plus 4 times 15.999. And on my calculator, I get 230.184. That's not exactly the same as this, but that is close enough. The difference has to do with the atomic masses that came off of my periodic table versus what came off of ALEKS's periodic table. Because this matches up, that tells me that this is my molecular formula.